So welcome to my talk. Today we present how I'm using SuriCata to play Attack-Defense capture-a-flag games more efficiently. So it's not the usual use case of SuriCata, and that's why I'm making a small presentation to show how and why I'm using SuriCata for this. So as a small introduction, I'm Ambre. I'm a reverse engineer at synthetizes, which is a French company located all around France. There is multiple departments, and I'm in Brittany, which is like on the Asterix map. As a pastime, I play a lot of CTFs. And I was a player at the European Cybersecurity Challenge in 2022, which is a challenge organized every year by ENISA, which is the European Cybersecurity Agency. Since then, because I really liked the challenge, I have been coaching the French team, which is called Team France. So I'm teaching them how to play Attack-Defense CTF with some advanced techniques. And this means that I'm teaching them SuriCata. And this talk is going to explain why I'm teaching them SuriCata to be efficient. So what is an Attack-Defense capture-a-flag? So SuriCon had a CTF this year that was a Jeopardy. So it's an online platform with multiple tasks, which are mostly independent. And you have one secret per sub-task, and the goal of the challenge is to find all the secrets. During an Attack-Defense, it's a bit different. You have machines to protect. So each team is going to have one or multiple machines. All the machines are going to be initially provisioned exactly the same. Usually it's a Debian machine with some Docker containers. And inside the containers, you're going to have 1 to 10 services with some intended vulnerabilities, which are placed by the organizers inside the services. So, for example, during 8 hours, you have to protect your services, find the vulnerability, patch them, and attach the other teams to steal their secrets. If I say this, you might say, oh, but it's easy, just whitelist the IP address of the organizers and block all the other IP address. It's not that easy, because there is a router in the middle of the network that does some traffic anonymization. So when a payload is coming to your service, you cannot say if it's legit or not based on the IP address. So, as you might guess from the name, there are 3 goals. The first one is to defend the service, to make sure that other teams are not able to attach your service and steal the secret. The second goal is to attach the other teams, to steal their secrets. And the third goal is to make sure that the service is still working fine. It's called service agreement. It's like an uptime. So there is not on one flag per service, it's multiple flags, and they are inserting regularly, like every 3 minutes, you're going to have a new flag. So when you attach, you have to attach continuously, and you have to defend continuously. There are multiple public events that follow this format, such as FAUSTCTF, ENOWARS and CTF, which are capture-a-flag events organized by German universities. So let's take a scenario to illustrate this. Here we have 2 teams. On the left, we have Montaigne, which is the national team of Switzerland. On the right, we have Team France, which is the national team of France. Let's say that Montaigne managed to find a vulnerability. They write an exploit for the vulnerability, and they're going to launch the exploit on all the other teams. So they are going to attack Team France. The payload is going to go through a game server, which is basically a router that is going to anonymize the traffic. And then Team France is going to receive the payload with an anonymized IP address. So this is really bad, because Team France is going to lose some points, so defense points. Team France is not attacking, so that's also bad. And third, if the attack is a DOS, like they are breaking the service, Team France is also going to lose some uptime. So we are very sad. So usually what people set up during the start of the CTF, it's a form of TCP dump. So for example, we are going to run a TCP dump on the vulnbots to have some sort of network capture. And then they are going to look really hard at the PCAP using word chart to try to see if they figure out some vulnerabilities from the network. If they find a payload exploiting a vulnerability, then they can patch the vulnerability. So it's defense by patching. It's very inefficient because in such events, the service tends to be written in very esoteric languages, such as Fortran or COBOL. So you don't really want to patch this. Sometimes it's even code source binaries without any symbols. So it means that you have to reverse the binary, find the code cave, then write some assembler instructions inside the binary to patch the vulnerability. So as you may have guessed, it's really hard. And if you do this, you might breach the service. So you're going to lose some uptime. While someone is trying to patch the service, another player from the team can replay the attack because everyone has the same services. You can steal the payload, change some bits of the payload, and send it back to all the other teams. That's a very efficient way of playing because you don't take the time to search for vulnerability. And it's an easy win. Yes, 2 years ago, we started using an IPS, so an intrusion prevention system such as SuriCata. This is very useful because it means that we no longer have to patch Fortran code, so thanks SuriCata. So it's also way more stable for the service because we don't have to restart the service, we don't have to patch the code of the service. So it means that now players are just writing SuriCata rules to block the payload. So yeah, as you may have guessed, we are now using SuriCata for traffic analysis, so an IDS scenario, and to block attacks, an APS scenario. So this presentation is about why we ended up choosing SuriCata for these tasks. So let's start with network traffic analysis. Usually people create backup, and when you have a backup, you want to open it in WordChart generally. The problem is that WordChart is packet level analysis, like you have 1 line per packet, so it's very inefficient during Attack-Defense CTF because it's very verbose and you don't have the time to go through the whole traffic. And the second problem is that many CTF teams are abusing WordChart a lot. For example, this is a network traffic from a Russian CTF team called Bushwhackers, and they are using a custom TCP client stack to mess with the TCP, to introduce corruptions. So the payload works, like it explodes the vulnerability, but if you try to follow the TCP payload in WordChart, you're just going to get a lot of garbage. So yeah, WordChart is not usable. The other problem is that players have too much information to process. They are stressed during such events. This is an average representation of a player. So we need a more reliable solution or a more concise solution. We are not the first of thinking about this. Some other teams already implemented tools to do that, such as Flower, Caron, and Tulip. All these tools are using GoPacket to do the backup loading on network analysis. The problem is that implementing flow tracking is very hard, and they are implementing by-hand things such as decompressing the HTTP payload. So, of course, there are multiple vulnerabilities, and sometimes they even make sure to make sure that the vulnerability is present in the open source version, so that if another CTF team is using the open source version, then they can just be abused by the team who wrote the tool. So last week on Twitter, someone complained about this and was able to exploit the tool. So yeah, that's a thing. So yeah, we don't really want to use GoPacket. We don't want to do things by hand. So let's use SuriCata. So SuriCata, if you run, for example, in replay mode on some backups, you're going to generate a file called ev.json. It's basically a log file with 1 JSON per line. It's 1 event generally per line. So for example, here, the first line is an alert event generated generally by a SuriCata rule of type alert. The second one is HTTP, which means that the HTTP decipherers of SuriCata found that this flow contains some HTTP traffic. And then in the JSON, you're going to have a URI, you're going to have multiple metadata about the HTTP layer, so it's really nice. It's much more higher level than WordChart. It's not packet, it's directly all the analysis. So it's robust. There are many desetters. The problem is that when we are applying an Attack-Defense CTF, we don't really have the time to play with GQ. So having a JSON is not efficient. So we utilize a tool that is automatically showing all the flows and making a summary for each flow in a way that is tailored to CTF. And if we have a flow that is not triggering any custom application protocols in SuriCata, we want some fallback to just printing the raw payloads. It's common to have services that are just speaking over netcat with text. So we wrote a tool called Shovel 3 years ago, which is basically just a bit of Python to do a web application, an SQL database with the data from ev.json, and a UI plugin to extract a bit more information from SuriCata. The idea of this proof of concept was to see if it's possible to write a SQL schema to efficiently query the ev.json by flow. And the answer is yes, and we are very efficient. We can just say, I want all the data from a flow, and the request is going to be really fast. 3 years later, now we have this monster, which is, compared to the other tools, are not that heavy. So the backend is running on SuriCata with 3 different plugins. We have 2 plugins in Rust. One is EV-SQL plugin, which changes the output format of EV to be SQL. So we can write, for example, a PostgreSQL database or SQLite. The second one is a plugin to change the output of file data. Rather than having some folders, we are directly writing a compressed archive. So a file data is compressed only if it's larger than, for example, 200 bytes. And then we have a very custom plugin that just dumps all the raw TCP and UDP payloads after the reconstruction engine as a fallback if the analysis was not didn't contain the information we needed. So this slows down a lot SuriCata, but it's still fast enough for our use case, so it's nice. And then we have some front-end, so we can use Grafana directly on the SQL data, and it works great. Or we can use a custom Python application that summarizes the flows. So we need an input to SuriCata. Usually we can put pcaps. The problem with pcaps is that it's going to introduce latency because you have to TCP dump on the machine, rsync the pcap, then put the pcap back into SuriCata. So we would like to do some traffic mirroring. The problem is that the Winbots is not a trusted machine. It can be easily compromised by other teams. So we don't want to put SuriCata in the analysis mode on it. And sometimes the Winbots only has a SSH access with no public address. So we want to have some sort of traffic mirroring that can just be set up through a SSH tunnel. Turns out that OpenSSH has an option called -w that makes a tunnel. And it means that you can create a TON5 tunnel, for example, or a TON tunnel, and then with NF tables you can dump the traffic from the game interface into the tunnel. It's very inefficient because you have an overhead, but it's fast enough for our use case, and it's robust. If the tunnel is too slow, it's going to print warnings in the console saying, oh, the buffer is filling up. So you have times to figure out why there is too much traffic being cloned. So yeah, we are not doing this, and we have like almost no latency compared to real time, so it's really nice. So let's do the demo. Yep. No Wi-Fi, great. Okay, so that's shovel. So on the left, you have a list of all the flows in chronological order. So you can scroll and you have a timeline showing you the start of the game with a blue line on where you are at currently. So you can teleport, for example, at the start of the game to look at, oh, I have a filter, I have to disable this. Up. So you can look at what was the flow during the start of the game. Then you can go to, for example, some more recent flows. And when you click on the flow, you have on the right a summary. It's all the data from ev.json plus the file data plus the raw periods directly under. So if there is an issue, we can just scroll and look at what was in the packet. And if you want an HTML, of course you can do it. And if you don't want this view to render, for example, the HTML, you can fall back to a more less concise view. But usually the more concise it is, the more efficient it's going to be for Attack-Defense, and it's better. So you may have noticed that I have tags on my flow, and I can filter using the tags. So for example, I can say I want all the flows with JPEG image. If I click on it, I'm going to have a JPEG. Yeah, that's a random service. So this is actually using Suricata rules. So it's a bit hacky. I'm using the metadata of rules to put the name of the tag on a color. And I can ship like 200 different rules into Shovel to make sure that if, for example, we have /TCP, we are going to have an alert, a tag that we can directly click on it. It's fast, it is powerful, and it's well documented, thanks to Suricata. And if you figure out something that is matching the traffic of an attacker, you can just copy it into the IPS to block the traffic. The problem is that if you want to add a new tag during the event, you must repair previous traffic to match the rule that you just added. Last week I had some issues with Suricata performance with the memcap of TCP assembly. So I ended up making a Grafana dashboard using the S-Trade data. So this is now open source if you want to query the Suricata stats. Here we can see in yellow the TCP reassembly and making sure that we are not reaching the memcap. So let's now speak about finding some Suricata flows, because of course when you put Suricata in front of some very offensive network traffic made by players, not everything is going to be fine. The problem is that players like to bend a lot the protocol specification. Players want to evade the detection. We have even the team of Netherlands that started some vulnerability research into Suricata. 2 years ago, they had a bypass of Suricata with the urgent, like in TCP, they were using the urgent to bypass Suricata during a live event. It is now fixed in Suricata 8, but yeah. Now players are looking into Suricata, it's fun. Also, the services are using some esoteric web frameworks, so you can trigger some weird issues with HIP HTTP. And also, we have new people introduced to Suricata, so sometimes they think outside the box and they tend to break some things, such as maybe a ticket opened recently. So, of course, we have players trying to evade detection. So, where is my cursor? Here. Up. So sometimes we have flow like this with many anomalies, like many, because it's a custom TCP stack that is just doing weird things with TCP. When it happened, if we really want the PTAP, we can click here, and it's going to download the PTAP to verify in our chart that it's really, like something is wrong. But if Suricata is able to figure out when a player is trying to do weird things. So for example, in my dataset, we have like more than 200,000 packet invalid timestamp anomaly. Like, players are trying to do things that breaks a lot of tools, but not SuriCata. Like, it's just raise an anomaly. It's nice. About HTTP, we have some HTTP anomalies. Last year, I had a service that was using content encoding identity. It was an ASP.NET service. It turns out that the RFC says that you should not use identity as a content encoding, but ASP.NET was doing it. So yeah, now SuriCata supports this. Another one, which is weird, is that some frameworks like to duplicate some HTTP headers, such as setCookie, vary, or date. And for example, for setCookie, it's Express, Django, and Tesray, which are like frameworks used by lots of people. So it's weird that it's an anomaly. So now there is a Redmine ticket for this. And also, sometimes we have weird anomalies because peers are trying to mess with a service. For example, when we have like unable to match response to request, it's because we have peers trying to smuggle some HTTP requests using the fact that we have an Nginx in front of the service. So yeah, it's really useful to have an anomaly system. A surprise we had with SuriCata 8. So when SuriCata 8 was released, there was a CTF like 1 week after. So we installed SuriCata from the Debian from the Ubuntu PPA as an IPS. We used it during the IPS, and 1 hour after the start of the event, we had a set fault of SuriCata, and many more set faults minutes later. Turns out that there was a weird issue when we were adding some rules into the IPS. And this is the patch fits in the issue. When you look at the patch, it's very hard to understand why it was breaking. And now I'm using this to show people that coding in C can be very hard. Some hints, of course, using Rust would have fit the issue. And also, SuriCata CICD did not catch the crash. The reason is that it's because of the Ubuntu PPA that has some compiler options, which cause an issue because here we have some types aliasing, and this is actually something that is undefined behavior in C. So yeah, I have a member of my team who wrote that took like half a day to look into it, and yes, it's not respecting strict aliasing, so it's undefined behavior. Yeah, it's very hard to write code in C. Yeah, I have other limitations. I started opening more tickets, but it's mostly like things that I find like. For example, for the first one is I'm doing regex to extract fields. And it turns out that you can only do a relative distance of 0. You cannot do a negative relative distance. It's because I have a weird use case that I'm triggering these limitations. So thank you for listening. The source code obviously is available on, as a GPL license because I use SuriCata. It's on GitHub. And if you want to try it live, I have some demo instances on shovel.afit.org if you want. Thank you.
Yeah, Giuseppe has a question.
Thank you very much. First, I would like to ask you which are the SAP false positive that you have seen? SIP messages that you have seen as a false positive.
I think it's because it was. Oh, sorry. I think it was because it was a custom TCP service that were directly speaking some text on Netcat basically, and they were using some text at the beginning that was triggering the SIP detector. So then we had an anomaly because it was not SIP. So during the event, we just when we had this, we just disabled the SIP using SuriCata.yaml. But yeah, it was something like it took some time to diagnose. So.
And You have seen it also false positive in Suricata 7 or Suricata 8?
I think it was Suricata 8.
Okay. Do you have any example that you can share? Because
I have backups. I don't remember which one, but I can try to find it. If you, we can talk later if you want.
yeah, sure. Thank you.
Any other questions? Philippe? Oh, Matt's coming to get you on the other side.
No.
Hello, hello. Yeah. So what do you mean for the plugin, and are your plugins public somewhere?
Yes, so the plugins are in the repository in the RGPL. So the issue with the plugins is that it was this. No, this. So for EV, there is a function to register as an output in EV. And the parameters of the function have like simple structures, so you can just bungee the thing on the interface is small enough to be feasible in Rust. For file data, it's also feasible, but if you try to do to register a custom output for the payloads, you have to have some internal Suricata structures that have some defines in it that change the length of the structure depending on how you compile Suricata. This means that if I do a Rust plugin and I don't know how Suricata is compiled, it's going to be problematic. So I don't have a solution for this. It would be nice to.
Neither do I.
It would be nice to have like a Suricata crate, like Suricata-API or something like this, but I just import in my Rust code.
There is a Suricata crate already.
Yeah, but it's the Suricata crate used inside Suricata, so it's very slow to compile.
Yes, I have the same problem.
And I don't want to compile this in my CI/CD.
Thanks. And so I'm working towards that step by step.
Thanks.